Let us continue our discussion of real scalar fields, and we started looking at quantizing the theory of real scalar fields. And let me remind you that we are looking at free field theory. Okay, all the terms are quadratic in the fields. Okay, so that the equation of motion is linear. So we are looking at free field theory, and last time we had written down the commutation relations. So if you promote the field phi to be an operator, so you put a hat here. Okay. In this lecture, I will not put a hat. It is understood that it is an operator. Okay. So we found that these are the commutation relations. So these are called equal time commutation relations because you see that t here and the t there are same. Okay, and then of course the conjugate momenta pi, they also commute. Okay, and then you have the field with its so pi is the momentum density, right? You have pi y t, and these are canonically conjugate pairs. And we saw that the Poisson bracket of phi and pi, if they were treated, when you're treating them as classical fields, that gives a Poisson bracket of which is equal to delta cube of x minus y. And when we quantize it, we have to put an IH bar. Okay, delta cube x minus y. Okay, that's good. Now I want to write down the Hamiltonian. Now that we have the momentum density with us, we can write down the Hamiltonian. And the Hamiltonian is written with in terms of the momentum density rather than the phi dots or q dots. And that's easy. We have already done the work in the last video. So you recall that the Hamiltonian is basically pq dot, where let me put alpha here. Okay. I'm thinking of any general system with several generalized coordinates which are labeled by alpha. So q of alpha are the generalized coordinates for that system, and this is what you have, minus the Lagrangian. Okay. Now if you look at what q alpha we had, let's look at that. Where are we? Yes. There is something not good here. Somehow h3 half is missing. Okay, so we saw here that pi is qi dot. Here's good, and then qi is defined to be h3 halves of phi. Okay, so here I had missed the h3 half. I'm sorry for that. Now it's good. Yeah, here I had used, but there I forgot to write. Okay, here it was fine. Okay, so now what I can do is to construct the Hamiltonian. I need the conjugate momentum pi, which is h3 halves of phi dot, and your phi dot is basically pi. Okay, so here we can have, when we are constructing the Hamiltonian, we will get, see, this q dot for this case will become p alpha. Okay, and in the Lagrangian also, when you put it, it will also give you half p alpha squared. So you will get half p alpha squared plus all the potential terms coming from the Lagrangian. So that's the generic structure. Now for our specific case, we have half summation over, let me first write P alpha. So P alpha is H 3 half of phi I, correct? Phi I of t. That's what we saw in the previous slide. And then I should square it. So this gets squared and becomes an H cube. This gets squared, of course, and you have to sum over all the lattice points and plus your potential term. Now, if you look at the first page, this is H cube, and you have sum over all the cells. That makes integral d cube x when you go to the continuum limit. And phi I dot is what is basically pi. So this goes over to the following. It becomes half integral d cube x squared. Okay, and the potential terms, they are easy. They come from the Lagrangian and they are simply this. What I can put here itself. Plus m square phi xt square. Okay, so that's the Hamiltonian we have. Let me write it down a little bit neatly. It's d cube x half pi xt whole squared plus gradient of phi xt whole squared, and this is a half, of course, and half m square phi square. Okay, that's the Hamiltonian for this system. Okay, very good. Now what we'll do is we will instead of working in the coordinate space or the x space, we'll go to Fourier space. Okay, so we want to do certain Fourier transforms and want to cast everything using these Fourier transforms. Okay, so that's what I'll do now, and you'll see that it is going to be very helpful. So let me define phi tilde kt, okay, to be a Fourier transform of the field phi, and the transform is with respect to the variable x. Okay, so phi x t e to the minus I k dot x. Let me not write dot. Or I can, there's no problem. And d cube x over 2 pi 3 halves. So I'm going to keep the factors of 2 pi symmetrically between the Fourier transforms of phi x and phi k, phi tilde k. Okay. Similarly, I define a Fourier transform of the momentum density pi, okay, d cube x over 2 pi 3 over 2 I tilde k t. Okay, these are just the definitions of Fourier transforms, and we can also write down how phi and phi tilde will be related. I mean, if I want to express phi in terms of phi tilde, they are related through the inverse Fourier transforms. Let me write it down here. So if you have phi xt, then you can write it like this: phi k t e to the I k dot x integral d cube k over 2 pi 3 halves. Okay, and the integration limits go from minus infinity to plus infinity. So you have pi xt, and again the same thing, d cube k over 2 pi 3 halves e to the I k dot x and pi k t. Okay, I should put a tilde here and a tilde there. Okay, it will be a good nice exercise to just check whether everything is consistent here. So what you do is start with the phi, substitute for phi tilde this expression, okay, and your right hand side should again evaluate to phi. Okay. This should be easy. See, when you are substituting here, so let's start with this right hand side. Let's do this, it's a minor exercise, but let's do for a warm-up. So I'm looking at this, pi xt is equal to d cube k over 2 pi 3 over 2 e to the I k dot x, and then I have phi tilde kt. Okay, so I substitute phi tilde kt, which is here, integral. Now I should not use x as the variable. Let's use y, because if you use x, that's a problem because you already have an x here. Okay, and anyway, the x in this expression is dummy, so you should be using something else. So let's use d cube y 2 pi 3 over 2. Okay, this is a simple thing, but should be kept in mind that you cannot use the dummy variable to be x here. That's a disaster. Then you have e to the minus I k dot y and phi yt. Okay, that's good. Now you can combine the two exponentials. It will give you e to the I k dot x minus y. Okay, so I have integral d cube k 2 pi 3 halves, then integral d cube y over 2 pi. Let me do it in two steps. It's not too much of writing. Okay, so I can combine these two. It will give me e to the I k dot x minus y. Okay, so these two. Then I can do an integral over k. So when I do an integral over k, I will use this. I will use d cube k. This thing of the exponential is just a delta function, but there is a factor of 2 pi cube. Okay, delta cube x minus y. Okay, so I get a factor of 2 pi cube, and that factor of 2 pi cube cancels with these 3 halves. Okay, so there is no factor of 2 pi left. I have a delta function, and the integral over k is gone. So you are left with integral d cube y delta cube x minus y times phi y of t. And now this delta function will just force the y to become x, phi xt. Okay, so we have also verified that everything is good with the Fourier transforms that we have defined. It was meant to be a minor exercise here. Okay, good. Then I will give you again some simple exercises to do, which you can do yourself. Show that if you take phi tilde kt and phi tilde k prime t and take the commutator of it, you get 0. Okay, that will be very easy to show because phi tildes are basically coming from the phi's, and apart from the integral and exponential factors, it's basically phi. And the two phi's commute, so correspondingly the phi tildes will also commute. And the same story for the pi. Okay. So this will also be obviously true. And similarly, it's also easy to verify that if you take phi tilde kt and pi tilde k prime t, you should get the following. You should get I h bar delta cube k plus k prime. Okay, note that it's not minus k prime. When you had in terms of phi's, you had a phi xt, pi yt, you had delta cube x minus y, but here you have plus, and this should be easy to check. Maybe, okay, even though it's easy, let me just show how to do this. So I'm going to show you this one. So phi tilde kt pi tilde k prime t. This I can write as, now phi tilde is the Fourier transform of phi. So let me write this with x 2 by 3 halves, and then you have e to the I minus I k dot x. Okay. So you see x is dummy, so this result does not depend on x. Okay, and similarly you'll get something similar expressions from pi tilde. Let me write down that also. Integral, and I should use some other dummy variable. Okay, because it's going to be multiplied with this one, so I should be using something else. Minus I k prime dot y, and then you have your pi yt. Okay, other than the phi and the pi, which are operators here, everything else is just numbers and summation, so that can come out, and you get integral d cube x 3 halves, integral d cube y 3 half, 2 pi 3 halves, and then you have e to the minus I k dot x, okay, times e to the minus I k prime dot y, and then the commutation relation gives you I h bar delta cube x minus y, right? The commutation of phi and pi. So I have I h bar, which I can put here, and I have a delta cube x minus y. Okay, that's good, which is equal to I h bar. Now let me do the integral over y. Okay. So I'm going to do the integral over y and use the delta function to set y is equal to x. Okay, so wherever I have y, I will put x. So this will make it x. Now these 2 pi I will combine, and I'll write as 1 over 2 pi cube. I have integral over d cube x left. The delta function will be gone when I do the integral over y, and this will become e to the I k dot, or let me bring out a minus, x Sorry, I'm doing something silly. No, everything is good. Uh, so it will become e to the ik dot x here. Let me write here e to the minus ik dot x. That is fine. And the second factor will become e to the minus I k prime dot x becomes y. Sorry, y becomes x. Okay, which is same as e to the minus I x dot k plus k prime. Okay, so here I should have, remove it, e to the minus I k plus k prime dot x. Okay, now you know that if you do the integral of this plane wave, that gives you a delta function and a factor of 2 pi cube. Okay, the same thing as we have seen before here, this thing. Okay. When I use it, 2 pi cube will be gone. I will be left with a delta function. So it will be I h bar delta cube k plus k prime, because your delta function will have this as the argument. Okay, so we have proved this last one also. Okay, so now we have our commutation relations expressed in the Fourier variables also. Now what I want to do is I want to write down the Hamiltonian using these variables, the phi tildes and pi tildes. Okay. And that's also fairly simple, straightforward exercise. So we start with our Hamiltonian, which is half pi, not a vector, square plus half gradient of phi plus half m square Okay, that's our Hamiltonian. Note that this does not have the structure of a Lorentz invariant quantity. There is a plus sign here, and this, even if you express in terms of the dots, phi dots, it will not have the structure of a Lorentz invariant quantity. Okay, and that is good. I mean, that's fine. There is no problem, because Hamiltonian is not a Lorentz invariant quantity. Okay, Hamiltonian gives you energy, and energy depends on the frame of reference you are in. Okay, so it would be actually, if it turned out to be something Lorentz invariant here, then you should be alarmed that you have made a mistake. So this is fine. Now, which one I want to do? Yeah, so I will not do all the parts of it because they are fairly straightforward. Let me just look at only this piece and show what it will look like when expressed in the phi tildes. And these will be then very obvious to see from what I do, that what the result will be. So let's look at the term, this one, second term, and express it in Fourier variable. So it's d cube x is a half gradient. So this is gradient phi dot gradient phi. That is what is gradient phi squared. Now I write, for phi I will write integral d cube k over 2 pi 3 by 2 e to the ik dot x, and then you have phi tilde k dot x, phi tilde kt. Okay, because phi tilde was defined with e to the minus ik dot x, and phi is defined with e to the ik dot x. So which is good. Then you have a dot product, and you have again a gradient here. d cube k prime over 2 pi 3 halves e to the I k prime dot x, and you have a phi tilde k prime t. Okay, here is this bracket is closed, and that's all. Now this is equal to half integral d cube x perfect. Okay, let me keep it this way. So integral d cube k over 2 pi 3 halves. Then when this gradient acts on this one, it will give you ik. Okay, so this, okay, see this is a scalar object as far as rotations is concerned. I'm not talking about Lorentz transformation. So k dot x is a scalar under rotations. This, because there is an arrow, that arrow is to signify that this transforms as a vector under rotations. So this entire object should be a 3 vector, and that's why you have a the result has a k vector. Okay, that's correct. So this one will give you ik. Then you have a dot product. Okay, and then this will similarly, when this gradient acts on here, it will give you minus ik, and these two will be dotted. So you will get ik dot minus ik prime, not k prime. This one gives you this thing. Okay, and then because you are taking derivatives over exponentials, they will give you back the same things. So here it will become e to the I k dot x phi tilde k t, and again the same thing, d cube k prime over 2 pi cube e to the I k prime dot x phi tilde k prime t, and then you have this vector ik dot minus, why I have a minus here? No, there should be no minus, sorry, ik prime. Okay, that is fine. Yeah, now you see you have e to the ik dot x, so there's an x here, e to the ik dot k prime dot x, so you have an x here, and I can do an integral over x because other than these two exponentials there is no other place where you have an x. So this integral is very easy because that gives you a delta function, right? So if I take this, and this, I will get a 2 pi cube delta cube of k plus k prime, okay, because they will combine together to give you k plus k prime. So my 2 pi cube will cancel these two factors. The integral will be gone over x, and these two factors will be gone and leave behind a delta cube. So let me write that down. So you have half integral d cube k over, okay, as I said, that's gone, d cube k integral d cube k prime, then you have a delta cube, delta cube of k plus k prime, and then that's all gone now, and then you have the two factors of phi tilde and this one, the k and k prime. So I have phi tilde, maybe I'll put the phi tilde at the end. So I have ik dot ik prime, and then phi tilde k t phi tilde k prime t. Okay, and this becomes half integral d cube k. Now let me do the integral over k prime. Okay, so doing this integral, because of this delta function, we will set wherever k prime appears as minus k. Okay, delta cube of k plus k prime hits when k prime is equal to minus k. So this k prime gets turned into minus k, and this k prime turns into minus k. Okay, and the integral over k prime will be gone. So I will have I square is minus 1. So I have a minus 1. Then k dot k prime turns into minus k. So I have minus k square. Okay, that's fine. And then I have phi tilde kt and phi tilde minus kt. So let me put the minus kt first. And phi tilde of kt. It doesn't matter. You can write in whatever order you want, because right now I'm treating the Hamiltonian as a classical. The phi is to be classical fields. Okay, and anyway, even if you treat them as operators, you have seen that they commute. So the minus goes away, and you have finally half integral d cube k square phi tilde of minus kt and phi of kt. Okay, so this was easy, and the other two are even easier because they don't even have a derivative. Okay, so whatever the effect of derivative was there in the calculation, that's gone. So you will simply have, instead of k square, you will have 1 here. Okay, because the k square was pulled out from the exponentials because of the gradient. So the first term here will give you half d cube k pi tilde minus kt pi kt. This we have done anyway, and this will give you half half d cube k m square phi tilde minus kt phi kt. So I can now easily write down the final result. My Hamiltonian would look like the following. D cube k. So you have pi tilde minus k t pi k t. Okay, or it's a bit, okay, fine, doesn't matter. Plus half, yeah, it's nicer to put half here. That looks, that way you don't forget the half. You have half, and then you had a k square, okay, coming from the gradient term, and the m square from that other term, and you can both take both of them and combine here, and you will get phi tilde of minus kt phi of kt, and this we will define to be omega k square. So your omega k square is k square plus m square. Okay, that's the Hamiltonian in terms of these Fourier transform variables. Okay, we will continue the development of the subject of quantization of real scalar fields in the next video.